So what we're doing right now is going through the portions of the lab that you will need to do and the portions of the lab that you will not need to do. I'm recording this just in case students absent and needs to go back and watch this. So they go through the details of how to set this up. I've got one set up already that we're going to look at here in just a few. And then they have you just detail the idea of constant motion being a position versus time graph. And they would have you use a motion detector to see that. And it was just to establish the idea of linear constant motion so that the next portion made more sense or contextually was good. Again, this is kind of an introductory lab. It just took me longer to build this than it did to get you to do the simulation for the lab 2 days ago. So 1 through 6 on page 6, you will not do. And then we're going to start with angular position and time data. So we will be doing this one. All right. So in this experiment, the photo gate was used to record the time. The cards block the photo gate. The data is shown in Logger Pro. We don't have Logger Pro, but I do have the data. I've taken the data and put it as a file. So if you look in the modules up under the lab document that is in day 3, what I've done is I've input something that says like rotational motion PVC lab data somewhere, something along those lines. And what I've done is I've just given you 2 charts. So this is angular position versus time data for PVC lab. So if you open that up, this is what we're going to be using. And I apologize that it is what it is, but it's better than not having the data because we can't really take the data. We're going to have angular position and time data for the rod. I don't know why I put O there instead of 0. But don't pay attention to computer time. Really, the times that we're paying attention to, this is the change in time from the beginning. This is the time you're going to pay attention to. The computer time is just used to do this. So we're going to have theta versus time right there. And then the second page is, again, theta versus time. All right, so we're going to have 2 theta versus time graphs here. You'll use the first one for the first graphs and the second one for the second graphs. All right. So I'm going to go ahead and switch back over so we can see. So that would be what you put in here. You'll just need to transfer that over. You can probably write it in or type it in. It's going to take you a second, but I do want the data in there for your benefit. I would have it open in a separate tab for when you're actually using it for the graph, so you can just switch back and forth, or maybe split your screen so that that's an option as well. All right, so then on the grid on page 7, and yes, I'm aware that this is page 6. I don't think it's counting the pre-lab. Create a graph of angular position versus time. Draw the best fit line for the data and determine the equation for the graph. Write the equation below the angular position time graph. So that's 5 and 6. 7 would be what type of motion is shown by the angular position versus time graph. It's asking accelerated or constant motion. All right, and you have to explain your answer using slope, right? That's what that's going to give you. Then determine the meaning of the slope and the y-intercept of the angular position versus time graph. All right, below the angular position time graph, sketch the angular velocity versus time graph. How do you get a velocity versus time graph from a position versus time graph? All right, derivative or the slope of the line. The slope of the line is how you're going to graph that second graph. Then below the angular velocity versus time, maybe you can predict what happens next. We're going to do an acceleration versus time graph. And how are you going to get the acceleration versus time graph? The derivative or the slope of the velocity versus time graph. Then 11 is compare the graphs that represent the angular motion of the rod to the translational motion of the string. Again, we don't have the translational motion for the string. It was constant motion. That's the takeaway that I needed to know, that it moved at a constant rate. So you would have a constant line. They're going to ask you to compare the 2 graphs. A hint, refer to the pre-lab questions. Make sure you measure the diameter and then determine the radius of the pipe in meters. So these are the graphs. You're going to have, so I want you to notice translational motion. Go ahead and draw in a constant line that has an intercept at 0. All right, because at 0 seconds, you've moved 0 meters. So you're going to then fill in the rest of the graphs. You guys remember the kinematic graph stacking? How do you do that? If you've got a constant slope of position versus time translational motion, what are you going to have for velocity? A flat horizontal line representing the slope at whatever value it was. There will not be values for this. It would be beneficial to have them, but you didn't take the data, so we're not going to use it. And then the acceleration versus time graph. If you have a flat horizontal line for the velocity versus time, what will you have for the acceleration versus time? You'll have nothing. You have zero acceleration. So that's going to be the graphs there. I'm just going to give you those. Now, the angular motion here will come from the data you have been given. Okay. So you're going to have to scale the graph. You're going to have to make sure it works. And I need it to scale. All right. So I want you to plot points. I want you to actually do this graph. It's not a huge graph. It won't take you that long. You didn't have to collect the data. You're just plotting the data. Okay. Once you get that slope, because you will calculate the slope, just do final minus initial. That'll be good enough. Then you're going to plot and make sure it's to scale, plot the radians per second. And then once you get the slope of the radians per second, you're going to plot the radians per second squared, the acceleration. All right. Do we have any questions about that part? Part's pretty straightforward. All right, then procedure 2, we're gonna wrap the string around the base. Be careful not to let the string wind under the bottom of the rod. Hold the PVC so it cannot turn. Hang a 200 mass over the edge, and then let it accelerate downward. So in the first procedures, if we look at what you did to begin with, you wrap, connect the string, line up one of the cards at the end of the rod, and then you're going to pull the block at a constant velocity across the table. So the way this works is originally you're pulling the block along the table at a constant velocity, and that will hopefully give you an intuition for what your graphs should look like. And then in the second example, we're going to hang a mass off the table. All right. So that mass hanging off the table will give us what? Acceleration. So this is going to be very similar to the pulley that we saw in the rotation or the moment of inertia lab. All right. So you're going to hang that mass off the table and then let it fall. So what I'm about to do here is I'm going to notice that there's a mass hanging off the table right there. I'm going to show you this here in just a second. I'm going to turn the camera around. I'm going to show you it moving. I'm going to put a mass on there. I'm going to increase the mass so that you can see the difference. Right now, it's not looking for like this lab is supposed to come before you know what moment of inertia is, but I'm going to show you moment of inertia in the process. All right, because I built it. We're going to use it for that purpose. Then you're going to analyze the data. You're going to take, you're going to plot all, or you're going to put those points that I've given you. That's the second chart that I gave you. And you're going to make a position versus time graph. You're going to write the equation. You're going to write what type of motion is shown in the position versus time graph. So again, it's either constant or accelerated. Or non-constant. Then below that, you're going to sketch the velocity versus time graph using that slope. Then you're going to use the velocity versus time graph to sketch so I want you to notice the word sketch. Sketch. There's two different words you can use in graphing: plot and sketch. Which one do you think is more accurate? Plot. So what do you think sketch means? Draw the picture. Draw me the picture of what it should look like. All right. This is where that data is. This is the position versus time graph. You're going to answer those questions. You're going to linearize the data. I wonder what that means. So you're going to have to square or take the inverse of one of the variables. You're going to plot that linearized data. And then you'll answer these questions. All right. Then you're going to take that data. You're going to plot it here, have the right variables as you go down. All right. So when you're looking at the page 16, when you're all the way at the very bottom, and you've got that 16, I want you to plot original motion. All right. Don't plot the linearized data. All right. So in this right here, I don't want your linearized data. I want your original graph. And then here, you're going to show me the derivative or the slope of that graph. Again, you're sketching it. And then here, you're going to have, you're going to have the slope of that line there. Okay. So really what we're doing here is we're going to be looking at the relationships between position, angular velocity, and angular acceleration. Do we have any questions? Not yet? All right, you've gotten the data. Go ahead and put that data in and start graphing. What I'm going to do now is I'm going to stop the recording because that's the instructions.